Hey everyone. In this last video, I want to summarize a few key points about simulation and the value of simulation for probability and understanding our models, okay? So we already used simulation in some of the previous videos, for example, the last one to kind of show the coverage probability of confidence intervals, but I want to summarize some key concepts here again, okay? Um, So just to give you a quick overview, why is simulation important? Ultimately, simulation can help us better understand the probability models that we use to mimic variation in the world, okay? And we already saw this in the applied examples that I showed you this week and in previous weeks, okay? Ultimately, we can use simulation to approximate the sampling distribution of the data, of our data that we're collecting, or relatedly of our statistical estimates, okay? And lastly, uh, ultimately, simulation is the most convenient and general way to represent uncertainties in forecasts, okay? Since our regression models are not deterministic, but rather produce probabilistic predictions, we can use simulations to convey and communicate the uncertainty around our models, okay? So ultimately, simulation is a crucial tool both to understand probability models, to understand kind of the implications of certain model assumptions, to characterize uncertainty by approximating sampling distributions given our assumed data generating process, and ultimately to communicate our results and specifically to communicate uncertainty around the estimates that we're trying to present, for example, in our papers and publications and so on. Okay. Another topic that is mentioned in your readings that I just want to briefly mention is bootstrapping, which is a really important tool. Just very briefly, the basic idea behind the bootstrapping approach is to use resampling from your available data with replacement to simulate a sampling distribution, right? So if you have a specific estimate or you collected a specific data set and you're able to construct a point estimate but can't directly construct uncertainty or estimates of like the standard error, or characterize the uncertainty around that estimate. One way to generate uncertainty or to approximate the kind of the sampling distribution around that estimate, that point estimate, is to simply resample from your available data, and for each resampling data set, for each resample data set, construct the same point estimate, and then look at the distribution of point estimates across bootstrapped samples, right? So that's a very general, very versatile approach that can be extremely useful. The advantage, of course, is that ultimately it's very general, right? Ultimately any estimate, as soon as you can compute a point estimate, you can create a bootstrap uncertainty estimate around that, right? Ultimately, all you need is an estimate and some kind of sampling distribution or some kind of sampling process that you can repeat again and again. But there are also limitations, specifically the fact that the effectiveness of the bootstrap crucially depends on the sampling protocol and the resampling procedure, right? So if you have more complex data structures like time series or hierarchical data and so on, then your bootstrapped standard errors and your bootstrap uncertainty estimates can be far off and can be very can basically make you think that there's a lot more precision than there actually is, or less, because it's not taking into account the underlying data structure properly. Okay, so the bootstrap is only as good as the underlying sampling protocol or sampling procedure, and for a lot of applications that have more complex data structures, the bootstrap can be misleading if it doesn't take into account these complexities of the underlying data generating process. Okay. So bootstrapping is it's an important concept to keep in mind. You'll see it sometimes in publications. We might talk a little bit more later on throughout the semester, but I just wanted to kind of briefly mention it so you're aware of that kind of in the context of simulation and the importance of simulation, because it's essentially another way of using simulation to construct uncertainty or compute uncertainty estimates. Okay. Another technique that is related to simulation that we're going to use more extensively throughout the semester is fake data simulation. And we essentially already did kind of some fake data simulation in the previous videos. And the idea behind fake data simulation, as we will expand upon in the upcoming weeks and months, is to basically evaluate the properties of the statistical methods that we're using based on our assumed data generating process. So we're assuming a data generating process. We have our specific models that we're trying to, or model specifications that we're using. And by generating fake data and running our models with these fake data, and then ultimately comparing these results to our actual, collected data, we can ultimately evaluate the appropriateness of our statistical models, right? So it's going to be extremely helpful, not in the sense that it provides insight into the data itself or the real world that we want to study, but it ultimately provides insight into our underlying models and our underlying data generating process that we assume in order to make inferences about real world events. Okay, so so those are all reasons why simulation is incredibly important in statistic and in data analysis. Okay, and just to wrap things up, I will go through one quick example that is kind of related to one of the examples on that was included in the simulation chapter in our textbook. Specifically, I'm just going to go through one example where we simulate probability models. Specifically, we're looking at simulating the height of random adults. Okay, and you could think of this as, then this is just one example that illustrates kind of more complex data generating processes that are more complex in the sense that they involve more than just one draw from a normal distribution, right? As we already learned in the height, weight, and normal distribution video a couple videos ago, we saw that the height of a population doesn't in of itself overall doesn't follow a normal distribution, because ultimately it's a combination of multiple normal distributions for, in this case, men and women. Okay, so we can kind of replicate this assumed data generating process and see how kind of our fake data then matches with under this assumed data generating process matches with the actual observed data. Okay, so how do we kind of simulate the average or simulate the height of a given population? The first thing we can do is we can just generate the height of one randomly chosen adult. And the first thing that we have to do, given our assumed data generating process here for height, is to determine whether that random individual is male or female, and the probability of being male is 0.48 according to census data, and so this is a simple random draw from a binomial or Bernoulli random variable with a success probability, if you can call it success, of 0.48. Then next, the height, the second step in this kind of more complex data generating process, is that conditional on the result of the initial Bernoulli trial is to take two separate random draws from two different normal distributions for a man or for a woman. Okay, here we have the average height of men is 69.1 inches. For women, we have 64.5 inches with respective standard deviation. So if this if-else statement suggests if male is equal to 1, then we take a draw from this normal distribution, and if it's equal to 0, then we take a draw from this normal distribution. Okay. So far so good. The next thing is we can kind of scale this up and think about, okay, how do we select 10 adults at random and compute the average height of those 10 adults, for example, right? This is we can kind of easily scale this up. All we have to do is we increase the number of draws here to 10. Then we have 10 draws from this Bernoulli random variable, and we use the same if-else command now just with n draws from this random normal distribution, either from 69.1 average height or 64.5 average height. Okay. All right. The next thing, so this is now just the kind of the example that was also in the textbook. Now we will kind of use this and transfer this to this idea of fake data simulation to kind of check our real data with, you know, our assumed data generating process. Okay, and what we're going to do here is we will simulate the height data from our previous example using this anthropology data set of the foraging population. And so what we're going to do is we will, df is that old data frame. We will now simulate data for the same number of observations. I believe it was 352. We take a random draw from binomial distribution, or we take n random draws from a binomial distribution with the same proportion of men as we have observed in our data set about and then we're using the same if-else statement to specify two different normal distribution, one with the average height for men and one with the average height for women. Basically using the same exact same logic, but now using the actual mean and standard deviation that we observe in our data set, right? And now the next thing we can do is we can now compare real and fake data, right? Now we can go back to our initial scatter plot, to our initial histogram and density of the observed population that was in that data set, and the height of men and women that were part of this population. And we can compare this to our simulated fake data set under the assumed data generating process that men and women both follow a normal distribution, that we have a certain probability of being a man or being a woman, and then an associated average height with a certain standard deviation. Okay, and then we can compare those two plots, as we will see right here, and we can see now by comparing. Now let me move myself out of the way. This is just a quick example where we can see that we basically, by kind of assuming a data generating process, gender that just incorporates gender and then average height by gender and then otherwise a normal distribution, we're making an assumption about the underlying generative model, right? And then we can, based on simulation, we can create fake data, and we can look at that fake data and then ultimately compare it to the data that we observe, right? And the key idea and the key takeaway point is that we can use this and this comparison to then evaluate to what extent our assumed data generating process is appropriate, to what extent our assumed model, our assumed kind of process that generates the data actually resembles what we observe in the real world, right? So this is a fairly kind of simple example, and of course here we see that although the overall shape of the distribution is fairly similar, there's certainly some deviation between those two distributions. We could kind of think about running multiple iterations of the simulation to see how large the deviations are. But to the extent that there are deviations, right, this is a clearly bimodal distribution, whereas here these differences are not so clear, which might suggest that there are additional factors in the distribution of heights in this foraging population that was studied in the 60s that is not included in our assumed data generating process, right? So this is kind of one key example where you can think about, okay, we have some observed data, we can assume a data generating process, we can assume some model, and then generate new fake data and then compare it to the original data, and that helps us understand how appropriate our assumed data generating process and model ultimately is to understand the real world. Okay, so going forward, of course, we won't do this with basic height distributions, but we will actually do this with model predictions, right? But the underlying logic will be the same. It's all about understanding to what extent our assumed data generating process kind of helps us understand the real world, or to what extent we're missing something important. Okay, and that concludes our videos for this week, and I'm looking forward to our next Q&A session.